Hey APCal class, we are going to start the last section of notes for Unit 3. So this is 2.6, and it's going to be, we're going to talk about inverse functions and then moving on to finding the derivative of inverse functions. So a quick review of what inverse functions are. So it says, recall from college algebra, a function can be represented by a set of ordered pairs. So if they just give us a real simple linear function here, set A is representing your domain, and set B would be a set of range values corresponding to those. So we would have this set of ordered pairs 1, 3, 2, 5, 3, 6, and 4, 7, just adding 3 to the input value. So if this was representing a set of ordered pairs that would fall on this function, and we wanted to represent, hey, well, what's the inverse of this set of ordered pairs? All we do is reverse the x and y coordinates. So we get, this inverse for f inverse is how we read this. Remember that little -1? It looks like an exponent, but it's read as f inverse. So if f is given here, f inverse is to just reverse all of the x and y coordinates. And that's always a characteristic of inverse functions, is that if xy is on f, then yx would be on f inverse of x, okay? So that's what they're kind of going to go into here. A function g is the inverse function of f if f of g of x equals x for each x in the domain, and g of f of x equals x. And so that's going to be that algebraic test to determine whether or not two functions are inverses of one another. Okay, so then they say here, thus the domain of f equals the range of f inverse. So in other words, you can kind of see that they switch spots here, where we had 1, 2, 3, 4 as the domain. Now on the inverse, that 1, 2, 3, 4 is now the y coordinates, making it the range. Okay, so just some characteristics there. All right, so yeah, so it's f of f inverse is going to yield x, and f inverse of f is going to yield x, as they tend to undo each other. So in example 1 part A, it says show that the functions are inverses of one another. So what we're going to do is we're going to do these two tests, and we'll since they're calling f and g, we're not necessarily saying that they're inverses yet, but we're going to show that they are. So we'll probably use this notation here: f of g of x, and then we'll do g of f of x, and if they both equal x, then we know, yes, they are inverses. So f of g of x. So remember, what that means to do is to plug the g function into the f function. So this whole expression here is going to go in for the x right there. So I'll have 2, and then I'll have the cube root of x plus 1 over 2, and then that's going to be cubed, right? Because that's what I have right there. So I got to cube that, cubed, and then minus 1. Now as I simplify, we're going to see things get, right, they cancel kind of inverse. I got a cube root and something to the third power, okay? They're inverse functions, they inverse, they cancel each other. So the cube cancels the cube root, and I'm left with 2, and then I just have the x plus 1 over 2 minus 1. And here I'm dividing by 2 and multiplying by 2. Again, those are going to cancel each other out. Now I'm left with x plus 1 minus 1, which the plus 1 minus 1 cancels, and I am just left with the x in that composition that I did this way, f of g of x. Now I need to do g of f of x, see if I get the same thing happening there. So now in this case, I'm going to go the other direction, and I'm going to plug this cubic function, 2x cubed minus 1. That whole thing is going to go right in for that x. Okay, so I'm going to have the cube root of 2x cubed minus 1 plus 1 all over 2. All right, so inside here, the minus 1 plus 1 are going to cancel. So I'll have the cube root of 2x cubed, put my index on there, over 2. Right? Now I've got the 2's canceling in that fraction, so those cancel out. I'm left with just now the cube root of x cubed. Simplifies down to x. So therefore, that's all we need to do to show. So we just need to say, I'm going to find f of g of x, I'm going to find g of f of x, show the algebra that brings them down to x for each of those. Okay, so that's kind of your algebraic test there. All right, and then another characteristic of inverse functions is with their graphs. To show, that two functions graphically that they are inverses of one another, what we're going to see is that they do have a characteristic where they're a reflection over the line y equals x. So if I were to just kind of, I'm going to do that in black. If I was to sketch this line y equals x, and then if I were to fold the graphs over on that, they should match up. So they are reflections of the line y equals x. And so what that means, if I was just making a table of some values for sketching these graphs, so if I input -1, 0, and 1 into my original f of x function here, this 2x cubed minus 1, I would get these ordered pairs. I get -1, -3, I get 0, -1, and then I get 1, 1. And if just by plugging those in, you can see that that's what you'd get. And so that graph, -1, -3, I've got a point down here, -1. Oh, I kind of missed that one, but it would be like right here. -1, -3, 0, -1, and then 1, 1. Okay, so that would be the purple graph there. And for sketching its inverse now, I know because they are inverses, I can just switch these ordered pairs around. So I can flip this one, flip this one, flip this one, and then I'm going to get a graph that looks something like this. Okay, and so we know that an important thing here that I want to point out is just when you sketch a graph and its inverse, that you have these ordered pairs that are just kind of reflections over that line y equals x. So like -1, -3 becomes -3, -1, and so on. 0, -1 becomes -1, 0. Okay, and so that's what this reflective property of inverse functions theorem is stating. The graph of f contains the point AB if and only if its inverse contains BA. Okay, and that's what we're showing here. Okay, so that's an important characteristic, especially when we start doing these derivatives of inverses. It's important to remember this because that's going to help us when we're finding the derivative at a specific point on the inverse. We're not going to do this activity. That's for a TI Nspire. Okay, so existence of an inverse function. So in order for a function to have an inverse, what we say is that it has to be 1-to-1. Okay, so that's what they see right here. A function has an inverse if and only if it's 1-to-1. We talked about this in college algebra last year. And what that means, in order for a function to be 1-to-1, it has to be, they call it strictly monotonic, but that just means that on its entire domain, it's either increasing the whole time or it's decreasing the whole time. It doesn't go like up, down, back up again. So like, for example, this function here, if we were to graph that on our calculator, we would see that it's increasing on its entire domain. It kind of, it has that cubic look to it, but it doesn't dip down and come back up. It's increasing the entire time. So this one we'd say yes, it's strictly monotonic, and therefore it does. So these 3 dots means therefore has an inverse. Okay. If we change this a little bit and we change that from a plus x to a minus x, that actually, and then up from a -1 to a +1, does change the look of this graph, and it does decrease. It increases, then it decreases, then it increases again. So in this case, and what we say there is in order to have it to be 1-to-1 and have an inverse, it has to pass the horizontal line test. This one would fail the horizontal line test because the horizontal line would cross it more than once. Okay, kind of like the vertical line test for functions. The horizontal line test is for whether or not a function has an inverse. You'd state, that's to test if it's 1-to-1. Okay, so not 1-to-1. It's not strictly monotonic because it does increase, decrease, increase. So no inverse for that one. Okay, so guidelines for finding the inverse function. We could probably just go through it, but basically what we're going to do is we're going to switch x and y around, and we're going to resolve for y. And then, this is for verifying that they are at the end. Okay, so the derivative of an inverse function, it says the theorem for continuity and differentiability of an inverse function. So this is just talking about some characteristics of the derivative of an inverse function. Okay, so it says let f be a function whose domain is an interval I. If f has an inverse function, then the following statements are true. Okay, so if the original function was continuous on its domain, then its inverse is also continuous on its domain. Okay, so continuity holds. If you have a continuous function, its inverse will also be continuous. All right. If the original function is increasing on its entire domain, then also its inverse will also be increasing on its entire domain. Okay, and we can maybe just look at what we did right here. Our original function was this purple graph, and that was increasing on its entire domain, and its inverse, the red graph, that's also increasing on its entire domain. So that's just one example, but that'll be true for any function and its inverse. Okay. And then also, okay, so if it's decreasing on its entire domain, then its inverse will also be decreasing on its entire domain. And finally, if the function is differentiable at c, where c is not equal to 0, I'll talk a little bit more about that, but You know, if the derivative at c was equal to 0, that would be a horizontal like tangent line there, whereas, you know, if we had its inverse, that would give us a vertical tangent line. So that's why, you know, vertical would be undefined, you know, so that's why they're saying it can't equal 0. So, but if f is differentiable at c, then f inverse is also differentiable at c, okay, as long as it's not equal to 0. That would be the one exception there. Okay, so there's actually 3 methods. I'm going to go through methods 1 and 2 in this video, and then in the next one we'll do method 3. Okay, so evaluating the derivative of an inverse. It says this method 1 works when it's easy to generate the inverse function. So this is the easiest way to do it, but as they say here, this is not common on the AP exam. So, but it's a good to start with this because it kind of gives us a general idea of what we're actually doing here and a kind of a visual of the graph in that. Okay, so it says find the inverse function by interchanging x, y, solving for y. Take the derivative of this new y, which is your inverse function. So that's going to be the derivative of the inverse function, and then plug in the k value, which is some value of x. Typo there. Okay, so pretty simple one. If f of x equals just x squared, and we're just going to be working with positive x values. So when we do the reason that we have to do that is because in order for it to be strictly monotonic, you know, just always increasing, you know, because if we did the whole x squared, we'd be decreasing then increasing, right? So this is why we have to restrict that domain. Okay, so then to find the derivative of inverse at x equals 4. Okay, so let's go through these steps here. So first thing, it says find the inverse by interchanging x and y, solving for y. So this is our original, so we're going to say instead of fx, we'll just call it y for now. And then we flip x and y around, and then we solve for y, right? So y would then equal the square root of x. Typically we'd say plus or minus, but we're restricting that to just the positive values for x there. Okay, so y equals the square root of x. So I'm going to say then, that's my inverse. So if this is f of x is x squared, f inverse of x is the square root of x, right? Or x to the 1/2 power. That's probably what we'd do, because now we're going to do the derivative of it. Now some of this notation looks a little bit weird because you've got all these little marks here, but you know, this is f inverse of x, and to do the derivative of that we say f prime, right? But so it's f inverse prime. So it's that this indicates the derivative of the inverse. Okay, so there's kind of a lot of little, you know, notations in there, but this is what you'll see for derivative of the inverse. Okay, so it's f inverse prime of x. All right, and so when we do that, we're doing the derivative of that square root, which is going to be 1 over 2 square root, right? So multiply the 1/2 down, you know, and it becomes, you know, this would have been, maybe just to add a little bit to that, this would have been 1/2 x to the negative 1/2, right? And that's kind of how we get to this, all right? And then we're evaluating it at x equals 4. Okay, so now that we've got the derivative of the inverse, we're going to do, you know, f inverse prime of 4. Okay, right? So that's where we're putting it in. So we're putting a 4 in here. And so we're taking 1 over 2 times the square root of 4. So that's just going to be 1/4. Okay, so there we've done what they've asked us to do. But let's just kind of analyze this a little bit further. So our original function that we were talking about was just x squared, where x was greater than or equal to 0. So that's my blue graph right here, right? The inverse of that is the square root of x, which is going to be this red graph. Those are pretty basic graphs. I think everybody's pretty comfortable without making tables that that's what they're going to look like, right? Okay, now let's think about what they've asked us to do. They said, okay, now find the derivative of the inverse, that's the red graph, right? The derivative of the inverse of f at x equals 4. Okay, so that's what we did right here, okay? And go back to what is a derivative at a point? It's the slope of the tangent line, right? So what they're telling us is the slope of the tangent line right here, I'm just going to draw a rough sketch of it. They're saying that slope is 1/4, okay? Now, what I want, I'm just going to kind of jump ahead a little bit here because this is a good spot to talk about this. What we're going to see as we continue to do this, so we have, you know, I labeled these 2 points, 4, 2 and 2, 4. And if we were to compare the slopes at those reflective points, what I mean by reflective is over the line y equals x, there's a relationship here. This slope and this slope are always reciprocals. So what that means is that the slope here, you know, is 1/4. We found that. The slope right here would be 4/1. Okay, and that's going to be an important characteristic as we go through methods 2 and 3. We're going to see that develop. Okay, but I just want to point that out here. All right. Okay, next one. It says find the derivative of the inverse. Now this one's a cubic function, and this one is oh, okay, I didn't really talk about method 2. This is one that we're not just going to be able to solve like we did before. So that's why we're going to jump into method 2. It says this method is used when finding the inverse of a function is difficult or impossible. So you can't really solve for y. So it says these are your steps. Find the inverse by interchanging x and y. Don't try to solve for y because it's not usually going to be possible to do. Okay, but what we can do, because we've learned implicit differentiation, we're going to find the derivative of y with respect to x implicitly, and then solve for dy dx, and it will be in terms of y. Replace the value of k for x in your inverse function. Okay, it says step A from above and solve for y, and then plug that value in for y in your dy dx. I'll explain this step D a little bit more when we usually what we're going to do for this, because sometimes you can't just solve it by hand. What I usually would do is look at a graphing calculator, and it's questions like this you're typically going to be able to use a calculator, or they're going to give you some tables of values to look at, so it'll be okay. Okay, so here's what we've got. This was our original function right here. F of x equals x cubed minus 4x squared plus 7x minus 1 at x equals 3 is where we're supposed to find the derivative of the inverse, okay? So following these steps, because if I interchange x and y here, I can't really solve for y. This is, pretty much impossible. So this is where we have to decide, okay, we'll use this second method where we do implicit differentiation, okay? So if I do the derivative of x, I get 1 here. And if I do the derivative here with respect to x, I'm going to have 3y squared, just using my power rule, but I have to put dy dx after that. And then I'm going to have 2 times 4, negative 8y dy dx, and then this would be plus 7 dy dx, and the constant would disappear. All right, so then I would factor out the dy dx from all of these terms, and then I'd be left with 3y squared minus 8y plus 7, so I would just divide by that, and that's how I would solve for dy dx. Okay, so this is how I'm getting my derivative. I'm really just taking 1 divided by these 3 terms, right? So it's 1 over 3y squared minus 8y plus 7. Okay, now I've kind of worked ahead here on this, but I want to explain this. So it says at x equals 3. Okay, now I did graph this on a calculator. I'm just going to pull this calculator open to show you. So the graph is going to look something like this, right? I didn't sketch it all that great, but it's going to look something like this. All right, so I've got some ordered pairs on here. I've got 0, negative 1. I've got like 1, 3, and I've got I think it's like 2, 5 maybe. We'll see it on there when I pull it open. But okay, so if I look at this, okay, so this is the graph. I'm going to pull open the table on that one's quick. So the table of values here, I've got, if I wanted to sketch it, I'd probably just grab these 3 points right here: 0, negative 1, 1, 3, 2, 5. Right? That's what I'd have. And then I would know that the inverse, and I did that one in red here. I would just flip those ordered pairs around, right? So instead of 0, negative 1, I'd put negative 1, 0. So that's what I've got there in that red graph. Instead of 1, 3, I'd put 3, 1, and instead of 2, 5, I'd put 5, 2. So I've got those points on there, right? So those are my graphs right there. Now, what they're saying is this. I'm supposed to find the derivative at x equals 3 on the inverse graph, right? So but here's the thing. When my derivative right here does not contain any x values, right? So I can't plug 3 in because there's no x to plug it in for. So what I need to do is actually figure out when x is 3, well, what's the y coordinate on that, on that inverse function, right? And so that's why I sketched this out here, because on my, when I look at that graph, if I go back to, I've got the table right here. What I need to do then is say, well, on my original graph, since I can't really graph the, this one, because I can't put, I can't enter y's in there into my graph. So I graph the original, I have to say, okay, well, I want where the x coordinate is 3 on my inverse. Well, that means that the y coordinate is 3 on the original function. And so this point right here, 1, 3, would be the ordered pair 3, 1 on its inverse. Okay, think about that. If 1, 3, this is my original f of x that I graphed here, then that's kind of what I'm looking for then. So if I graph that original f of x and they say, hey, evaluate that at x equals 3, that means I have to say, okay, well, on the inverse graph, that's going to be the y coordinate 3. And then the x coordinate 1 here is actually what I'm going to be plugging. I'm going to plug that in because that's going to be my y coordinate since I have y's here. So I hope that makes sense. So that's why I put this here. The point on the inverse is going to be 3, 1, since 1, 3 is on F. Okay, so that's kind of an important idea right there. Okay, so I'm going to be plugging in 1 here and here, and so that simplifies to 1/2 then. Okay, so visually, what that's going to mean is, when I do that derivative of the inverse at 3, 1 right here, I'm going to have a slope right here of 1/2. And, an important, tie between on that is that at 1, 3 right here, the slope of this tangent line would be 2, right? So right here, my slope there is 1/2, which means that the slope right here of that tangent line would be 2/1. Okay, they're always reciprocals at those reflective points. All right. Example 5, this will be the last one we do. I know it's getting a little bit long. Sometimes AP, they kind of like to grab some of these, E and ln functions. And so same concept, we can still use method 2 on this. So when I do switch x and y around, right, so I have x equals e to the y plus ln of y. And then if I do the derivative with respect to x, I would have, this would be 1 on this side. And that's typically what happens, when we just flip them like that, we're going to have 1 here. So we end up 1 divided by whatever we've got left over here. Derivative of e to the y is e to the y, but dy dx, and then the derivative of ln, remember, is 1 over, y, dy dx again. And so I'll just be dividing by e to the y and 1 over y. And so I've got 1 over e to the y plus 1 over y. And now on this one, it's a little bit trickier to grab an ordered pair because it's e, which is an irrational number. But I think we can kind of figure this one out. So if I'm supposed to do it at e when x equals e, and so I'm putting e in for this x, right, right here, and I need to solve for that y because I need to have a y value to put in there. And so if I put e in for that x, and I'm like, okay, well, how would I get this to be equal to each other? Well, here's e to the y. I think I need it to just be e, right? So if I let y equal 1, that's e to the first. And then remember, ln of 1, or any log of 1, is always 0. So the value for y here has to be 1. Okay, so then I'm going to plug in, so it's E1 would be the ordered pair there. And so when I plug that in, you have to put a 1 in there, and my answer would just be 1 over E plus 1. Okay. All right, so that's going to be it for this video. We'll do method 3 in the